Hello everyone, my name is Rohit. Today I am going to present my semester project that is titled as Sysmon, a Linux process monitoring tool. This project is developed as a part of my MSc Computer Science curriculum. Before I go into the technical details, I want to clearly state the intention behind this project. The goal of Sysmon is not just to show process information but to understand how Linux internally manages process and how this information is exported to the user level programs. Most of us use commands like top, ps or htop regularly, but very few people actually know how these tools obtain their data from the operating system. So instead of simply using an existing tool, I decided to build a process monitoring tool built from scratch. Modern Linux systems are multitasking systems. At any given time, hundreds of processes are running simultaneously. This includes user application, background services, system daemons, and kernel threads. Although Linux provides tools like top, ps, and htop, these tools abstract away most of the internal details. You can actually find that the data has come as a final output, but we cannot state how this process are stored in the Linux internal file systems. So our main problem for the project is how can we design and implement a Linux process monitoring tool that can actually help us to interact with the kernel and clearly demonstrate what and how the processes are extracted. Objective of this project is to retrieve real-time process information directly from the Linux kernel, that is the proc directory. A second is to calculate CPU usage, and the third is memory usage using RSS. It represents the actual physical memory usage. The fourth is to provide a graphical user interface that allows a user to usually visualize the data, and also they would have some process control operations such as killing, stopping, and resuming processes. Finally, the most important objective is to learn and how front-end and back-end component interact in the real systems. Now I will explain overall architecture of the project. Sysmon follows a client-server architecture. Even though it runs on a single machine, the project is divided into two major components. First, the backend. The backend is written in the C programming language. The backend is also responsible for interacting with the Linux kernel, read process information, calculate the CPU usage, calculate the memory usage, and also perform the control operations. The second major component is frontend. In frontend, I have used Python using PYQt as my main language. The frontend is responsible for displaying data, handling user interaction, visualizing system statistic. The frontend and backend communicate using a UNIX domain socket. UNIX domain socket are used instead of network socket because the communication is local, faster, and it avoids unnecessary networking overhead. This separation of responsibility ensures that system level logic is isolated in the backend and user interface logic is isolated in the frontend. Now I will explain how the project starts and how the execution flows. When the project is started using the command make and then make run, the backend is launched first. The backend initializes itself by creating a Unix domain socket at a predefined path. Once the socket is created, the backend enters a waiting state. It waits for the request from the frontend, and this stage the backend is idle and not consume CPU resources. After the backend is running, the frontend application is started. The frontend starts initializing the graphical user interface and immediately requests process information from the backend. This establishes communication between the frontend and backend. After we execute make run, the execution of the backend starts from the main.c file. The first operation performed is the creation of a Unix domain socket. This socket is bound to the path at the temporary location named as sysmon.sock file. Once the socket is created and bound, the backend starts listening for incoming connections. The backend then enters into an infinite loop. Inside this loop, the backend waits for the client connection using the accept system call. The design ensures that backend is event driven. The backend does not continuously run in a loop during unnecessary work. It only wakes up when a system call is performed or the frontend calls him. If the command is get process, the backend initiates the process data collection workflow. If the command is kill, stop, or resume, the backend sends the appropriate POSIX signal to the target process. After the processing request, the backend sends a response and returns to the waiting state. This is the proc.c file, which is responsible for collecting process information. Linux provides process information through a virtual file system called as proc directory. The proc file system does not exist on the disk. It is dynamically generated by the kernel. Each running process has a directory inside proc, named after its process ID. Not all entries inside proc represent processes. Therefore, the backend filters out only the numeric values directory name. Each numeric directory corresponds to a running process. For each process, the backend reads the file, which is a proc directory, inside which a numeric PID directory, and after that a stat directory. This file contains detailed information about the process in a single line. From this file, the backend retrieves the process ID, its parent process ID, its process state, and the CPU time spent in a USSR mode. It also takes the CPU time spent in the kernel mode. The CPU time values are cumulative and measured in clock ticks. Memory usage is retrieved separately from proc PID status. Specifically, the VMRSS field is read. RSS represents the amount of physical memory currently used by the process. How the CPU usage is calculated. Linux does not provide CPU usage as a percentage. Linux provides cumulative CPU time values. To calculate the CPU usage, the backend uses a snapshot-based approach. The backend stores the CPU time values from the previous request, and when a new request arrives, the difference between the current and the previous snapshot would actually represent our CPU intervals. This difference is divided by the total CPU time of the system and also multiplied by the CPU cores. This ensures that CPU usage is correctly normalized on the multi-core systems. That is the same approach used internally by the tools like htop. And the next file is JSON file. After collecting all the process information and calculating the CPU usage, the backend format the data into the JSON format. JSON is chosen because it is a language independent and easy to parse. Each process is represented as a JSON object containing PID, PPID, process state, CPU usage, and memory usage. The complete list of process is sent as a JSON response to the frontend. After sending the response, the backend closes the client connection and waits for the next connection. About the frontend of Sysmon, it is implemented in Python using PYQt. It does not interact with the kernel directly. All the system level operations are handled by the C. The frontend focuses entirely on displaying information, handling user input, and visualizing system statistics. The execution of the frontend starts from the main.py file. It initializes the PYQt application. It creates the main window and initializes the user interface component. The main window consists of a dashboard and it displays the CPU and memory graph, a table displaying all the running processes, and a detail panel showing information about the selected processes. The frontend also initializes a timer. This timer triggers every 2 seconds. Each time the timer triggers, the frontend sends a get process request to the backend. The backend responds with the updated process information. Now let's visualize our project. First, we have to type the command make. After the execution of make command, just run make run. It will actually take us to the dashboard of the project. We can actually find there are four main sections. First one is CPU usage, second is memory usage, third is process detail table, and fourth is the process information table. We can see that the CPU usage graph is beyond 100 just because this system is multi-core. The memory usage shows us how many physical RAM is occupying of the system. In the third column, we can actually find there are many processes which are running currently. After checking, we know that the Python 3 using and OBS using most of the CPU usage. And after clicking on any of the process, we can find its information. The first information, its name, PID, its parent process ID, its state, its CPU percentage, its memory percentage, its parent name, and all the children names. After, we can actually find there are many of these processes. As we can see that our project is running successfully. Let's now just see what the action buttons do. So to check whether the action buttons are working, let's just add a new process. I add a Google Chrome process, and after I just click on an hyperlink, it starts reloading. After it, we can see it is an operable web file. So we can see that Chrome extension has been appeared here. Now if I just tap on stop button, a dialog box appears. We can see that the Chrome is not functionable now. I cannot tap anywhere on that, and we got a dialog box that Google Chrome is not responding. Let's just resume the process again. Again a dialog box appeared. Now we can see that the message has been gone and we can operate the file. After I just tap on the kill button, we can see that the Google Chrome has been closed. So our main functions have been working. So I would like to conclude my project as it is a process monitoring tool which is designed to demonstrate the operating system concept in a more practical way. In the future, this project can be extended to include process tree visualization, disk and networking monitoring, logging and alert system, performance analysis systems. Thank you.